Okay, so in lecture, we laid up there with this example here, we're talking about type 3 compounds, which again are different than type 1 or type 2 because they are really covalent molecules sharing of electrons here. So we do use prefixes, and as I mentioned before, these really should be the ones that should take you really the quickest. So if we look at this one here, we're working on at the end. I is a nonmetal, O is a nonmetal. So as soon as you see that, you don't have to worry about balancing anything, figuring out anything. Just pretty much need to use the appropriate prefixes. So there are 2 iodines. So the prefix for 2 is di. And again, on the first name, we use the entire name there, iodine. The next one is 7. The prefix for 7 is hepta. And oxygen does get the IDE at the end of it. We will, in this case, get an A and an O that backs up to each other. So we will get rid of that A off of the prefix that would be right there. And we end up with diiodine heptoxide. Again, the 2 I's are okay in this particular case. Same thing if we look at the next one, CO2. Carbon is a nonmetal, oxygen is a nonmetal, so we could just roll right into naming it. There's only 1 carbon, which means the prefix would be mono, but we do not use that on the first name. So we would just use, in this case, the whole name, which would be carbon. There are 2 oxygens, so the prefix for 2 is di, and that would be dioxide. So carbon dioxide in this case. Any question on those 2? Rolling to the last one, same thing. We see phosphorus, which is a nonmetal. We see Cl, which is also a nonmetal. So again, we have 1 phosphorus, so we will not use mono on it. So we'll just use the whole name there, which would be phosphorus. Prefix for 3 is tri, and again, the second guy gets the IDE at the end of it. So this would be phosphorus trichloride. Any questions on any of those names? At this point, which I think is probably the easiest of anything that you do, is actually the next thing. Once you start reading the name, you see di and you see penta, basically, that should tell you it's a type 3 compound. You pretty much just need to write what it says. So di is 2, nitrogen is N, so N2. Penta is 5, oxygen is O, and that would be an O and a 5. Again, nothing to balance here other than to just write what it says in terms of the prefix. When we look at the next one, carbon tetrachloride, again, no prefix on the first name, but we do see it on the second, which does tell us it is going to be a type 3. The no prefix on the first name tells us that we only have 1 of them, so that's all we should draw for carbon, all right. Tetra is the prefix for 4, and chloride is Cl, so it'd be CCl4. Again, the nice thing about these, no charges, nothing to balance, just pretty much need to write, what is there. Lastly, we see dioxygen and trisulfide. So the di is 2, oxygen is O, tri is 3, and sulfide is S. So O2S3. Any questions on type 3? Personally, I think that it is really the easiest out of all the naming, but it is unfortunately the thing that people screw up the most on. They really do screw up on these for some reason. They want to put like Roman numerals and all kinds of other things going on. Any questions on that? So as you see here, again, no Roman numerals, just prefixes. Before we had Roman numerals, no prefixes. If you find yourself Roman numerating and prefixing together, you probably are going to be wrong. There's only like a very weird place or special place where that could happen. So type 1, you don't need Roman numerals, don't need prefixes. Type 2, you need Roman numerals, no prefixes. And type 3, prefixes, nothing other than those guys. Any questions on any of that naming there? Okay. So a reminder as well, as we talked about type 1, type 2, they are ionic compounds. We've got our positive, negative guys. And as we talked about, again, it is that metal that is the most important. And type 3 here, pretty much all you need to do is count the proper thing and use your prefixes. All right, the next type of compounds we're going to talk about naming involve what are referred to as polyatomic ions. Polyatomic ions are basically groups of nonmetals that are held together by actually covalent bonding, sharing of electrons, but they actually do have an overall charge. So they're kind of a weird case. They are ions, but they are technically held together by internally by sharing of electrons. So for example, if we take something like NH4NO3, this is actually two polyatomic ions together. It would break apart right about there. Guy on the left is actually what is referred to as NH4 plus. That one nitrogen and that four hydrogens, they all stay together and it has an overall charge of +1. On the right-hand side is NO3, which is actually NO3 minus. Same thing here. That one nitrogen and those three oxygens, they stay together. They never break apart. They move around as a whole unit, and they really have a -1 charge. We actually saw both of these when we were talking about bonding. These are actually things that are sharing electrons. If we were to draw the Lewis structures, this right here is NH4 plus. Again, the nitrogen and the hydrogens, they're all sharing electrons. And that's really why they never break apart individually into hydrogens and nitrogens in this case. They move around as a whole unit. We also drew the NO3 minus, which looks something like this. So polyatomic ions are groups of non-metals that oddly do share electrons, are covalently bonded, but they end up with an overall charge. So they are still considered ions. And in this case, they pretty much are considered ions, which means we're going to put our positive and negative guy together. So when we do put it together, we ultimately are putting together something with a +1 charge and something with a -1 charge, which is why when we look at the formula on the next page that we saw, we just needed one of each of them. It really does follow the same sort of ionic idea of making sure we get to 0. So obviously +1 and -1 gets us to 0, even though there's a lot of elements involved, but they are really just two ions that are actually coming together and are held together. The two ions are held together by that opposite charge. Now, polyatomic ions, they do have special names. So NH4 plus is what is known as the ammonium ion. NO3 minus is what is known as the nitrate ion. The good news is with polyatomic ions, no matter how many you have of them in a compound, you just use the name. So if we were to name this guy NH4 NO3, we would just simply put both of those names together in this case, and this would be known as ammonium nitrate. So ammonium nitrate would be the name of this guy, simply just taking both polyatomic ions and names and putting them together. Now, when we deal with polyatomic ions, as we will see in just a second on this list of polyatomic ions, and you have one in your book and so forth, for the most part, most polyatomic ions are negatively charged. There are a few that are positively charged, but a vast majority of polyatomic ions do carry a negative charge, which means in most cases, what ends up happening is the polyatomic ion actually ends up hooking up with a metal, and you end up getting like a metal and a polyatomic ion that kind of come together. The importance of that is, as we talked about earlier, whenever a metal is involved, that is really the thing that you want to look at. And the same thing occurs here when we're dealing with polyatomic ions. And we go back really to, in most cases, using our type 1, our type 2 sort of naming. So a lot of times, because a polyatomic ion will be hooked up with these metals, if the metal is a fixed charge, you still don't need a Roman numeral like we did earlier. So you would just use the whole name of the metal and the name of the polyatomic ion. If the metal, like we saw earlier, does need a Roman numeral, you'll need to figure out the charge and use the whole name of the metal, Roman numeral for the charge like we did earlier, and then the name of the polyatomic ion. So the good news is a lot of polyatomic ions will sort of fall into type 1 or type 2 sort of naming. because they will find themselves hooked up with a metal. Any questions on that there? All right, the bad news about polyatomic ions is there's their list and a table, and you really pretty much, the best way is you got to bite the bullet and memorize pretty much the names and the charges that go with the polyatomic ions. Now, there is a way that can make it easier for you to sort of figure out charges and names and all that. And there are things that are related to each other. So there are some things on this list, for example, that has the same number of oxygens. I'm sorry, the same number of charge, but different numbers of oxygens. So we have something like NO3 minus, NO2 minus. Again, the NO3 minus has a -1 charge. The NO2 minus has a -1 charge, and that is these names right here, nitrite and nitrate. We also see a similar thing between SO3 2 minus and SO4 2 minus. One is ITE and one is ATE. So when you have a group of two that are related to each other, and really the only difference is the number of oxygens, the one that has the most number of oxygens, you will typically end in ATE. The one that has the least number of oxygens will end in ITE or ITE. So that's a really good way to sort of memorize some of these polyatomic ions. And sometimes people will go, I'll just memorize all the 8s. And if I need an ITE, it's 1 oxygen less. Everything else is the same charge, same everything else. Or people will remember the ITEs and know that the 8s are basically 1 oxygen more. Again, everything stays the same. Other common things that we see here are, and we'll go through some of these here, I think. There are actually groups of 4 that are related to each other. And this is the most common one, a group of 4 that we see, which is ClO4 minus, ClO3 minus, ClO2 minus, and ClO minus. Every single one of those has a -1 charge. Again, the only difference, if you go through them, is the number of oxygens there are. And we could kind of follow the same pattern. This is a pattern of 4 that are related to each other. And if you break it apart right about here, everybody to the right has the least number of oxygens, which means they should end in ite. So this should be something like chlorite. And this also should be something like chlorite. Obviously, you cannot have the same name for 2 different things. So in a group of 4, the one that has the least number of oxygens ends in ite and starts with hypo. So that guy is hypochlorite and chlorite. On the left-hand side are guys of 4 that have the most oxygens, so they should end in ate. So that is chlorate. This would also be like chlorate. Again, same idea. You can't really obviously have the same name for 2 different things. In a group of 4 that are related to each other, we put per in front of it, and it becomes what is known as perchlorate, chlorate, chlorite, and hypochlorite. And again, that's a group of 4 that are basically related to each other. So that's the additional thing that we do when you have 4 that are related. Cl is a halogen, and you could actually swap out the Cl for anybody in group 7, and they're named very similar. So instead of, say, ClO3 minus, I had BrO3 minus. Instead of chlorate, this would be bromate. So you can kind of swap it out. If you had IO3 minus, that would be iodate. So again, you can kind of swap out that guy for anybody in group 7, and they kind of change the name with the guy that's there. But that is the most common group of 4 is the perchlorate, chlorate, chlorite, and hypochlorite. Now, another very common thing that occurs is, if you look at that list, is we will sometimes put an H plus onto something. So CO3 2 minus, which is carbonate, it's a very common example. That is carbonate. If we put an H plus onto it, that gives us HCO3 minus by adding an H plus. And basically put hydrogen in front of it. So the name reflects that. This is what is known as hydrogen carbonate. And if that's not enough, sometimes people do not use hydrogen for hydrogen carbonate, but they sometimes just call it bicarbonate. So the bi basically is the hydrogen part that is put onto a polyatomic ion. We also see that with sulfate. If you take sulfate, which is SO4 2 minus, and put a hydrogen on it, H plus, HSO4 minus, we get what is known as hydrogen sulfate, are also sometimes referred to as bisulfate as well. So that's a very common two kind of bi names there, bisulfate and bicarbonate. By the way, when we talk about putting a hydrogen ion on, it is a hydrogen with a +1 charge, so it does affect the overall charge of the original ion. That's why it went from -2 to -1, because +1 and -2 gives you a -1 left over, so it does affect the charge. So on that list, that's a very common sort of thing that you do see is, you know, they put an H plus in front of something. Other ways, again, as I talked about earlier, for the most part, in a group of two that are related to each other, 8 has the lower number of oxygens and 8 has the most oxygens. A vast majority of all polyatomic ions will end in ite or 8, but there are some that actually do end in IDE. So for example, OH minus is actually hydroxide. CN minus is cyanide. So there are a few polyatomic ions that actually still end in IDE. And again, just sort of memorization is probably your best approach on that. Take a look back at, let's go back on that table, where'd it go? Okay, so let's see here. That's peroxide on the bottom right there. As I mentioned earlier, you really will never use, like I said, a Roman numeral and a prefix together. And I did say there's one spot where that could happen. And this is the spot where that could happen. And that is because the polyatomic ion itself actually has a prefix in the name, like dihydrogen phosphate or something like that. You know, something where the prefix itself, dichromate, has an actual prefix in it, or the polyatomic ion's name is a prefix. You could use a Roman numeral and a prefix at the time, but that's the only spot where that would occur. And it's really because that's the name of the actual polyatomic ion. So when we look at these guys, like I said before, you can see that, you know, NH4 plus is probably the only positive guy that we see there. NH4 plus, which is ammonium, should not be confused with ammonia that we talked about earlier. That's NH3, no charge. So those are two different things and very commonly confused. Because they are mostly negative, like I said, we will end up with sort of a type 1, type 2 situation. So if I had NaNO3, we would look at this and see that this is Na, which is sodium. NO3, once you kind of learn it, will be nitrate. So again, because the metal's involved, we would want to look at it and determine, should we use a Roman numeral? And should we use a Roman numeral here with sodium? Does sodium need a Roman numeral? It does not. It is group 1, is a fixed positive charge, which means we simply could roll to the name of sodium. And then again, we use the entire name of the polyatomic ion, which would be nitrate. Now, let's say we had FeNO3 2. When we look at this, FeNO3 2, Fe is iron, which is a metal. NO3 is still our nitrate. With iron, do we need a Roman numeral? We do. It's a transition metal. It could have multiple charges. So you want to kind of approach it the same way. Once you learn the polyatomic ions, you'll know NO3 is NO3 minus, which means there's not one, but two of them, which means it has a -2 overall. The iron here would then need to have a +2 to balance it out. and we would proceed to name it like normal. This would be iron, Roman numeral 2, because of the charge. And then even though, just like in type 1 or type 2, even though there are 2 of these polyatomic ions, it does not have an effect on the name. We just use the name of it, which would be nitrate. So iron, Roman numeral 2, nitrate. Same rule. The 2 is for the charge that is on the positive guy. Questions on that? Yeah. Yeah. The definition of a polyatomic ion is actually the guys that are on the list, and they really are groups of nonmetals that are really held together by sharing of electrons that have an overall charge. So that is really what the polyatomic ion is. It's actually like the nitrate part in this example up here. It is the polyatomic ion part. Yeah, so because it's an ion, it will make an ionic compound, basically is what all these are here that we're looking at. They're ionic compounds where the polyatomic ion in this case is the anion, and the positive ion is the metal in this case. And that happens a lot because, like I said before, pretty much all of them are negative. So in order for them to kind of bond to something and make an ionic compound, they need something that's positive, and that pretty much leaves metals that they're going to come together with. Not 100% of the time, because you do have ammonium that's positive, and there's hydronium, which is positive, but a vast majority of the polyatomic ions themselves are negatively charged. So when they do form ionic compounds, it usually a lot of times is with a metal. It has a lot to do with really the distribution of electrons overall in that molecule when they all come together, and the unequal sharing of those electrons. And they create something that we don't really talk about in here is things like we're referred to as formal charges on individual ions as a result of sort of the sharing of electrons. So when we look at something, where did I draw that guy here? When we look at something like nitrogen here and the oxygens that are in here, there are what are referred to as formal charge, which basically means nitrogen has 5 valence electrons. In this example, it has no non-bonding electrons, dots on the central atom, and you take half of the number of bonding electrons, which are there, which are 8, which means in this sort of orientation, the nitrogen, because of the way it's sharing electrons, has like a +1 charge. You could do similar calculations for the single bonded oxygens, and what they will end up with is a -1 charge each. And the double bonded oxygen actually ends up, because of the way they're kind of sharing electrons, with like a 0 charge. And if you add up all the kind of the individual elements within the bonds that are being shared, they take on an overall charge of 0, -1, and +1 cancel each other out, leaves you the -1 charge that's left over overall. And it's a result of sort of the unequal sharing of electrons, or how the electrons are shared when they are in a covalent compound. That sometimes what it results in is really like an overall sort of charge that occurs. Yeah. And that's kind of the same thing that happens over here with our nitrogen. Same thing happens is the nitrogen here has a +1 charge. Each of the hydrogens in this arrangement is pretty good. It has like no charge, and that's where the +1 overall charge comes from. And that's what's referred to as formal charge, which when you go to 1A, you'll learn how to kind of calculate that and stuff like that. Yep. Other questions on that? So they are kind of a weird thing in a sense, because we think about trying to sharing of electrons as, we're not going to create things that have charges or anything like that. But the way they're able to share electrons sometimes will determine whether or not the overall thing does have a charge or not. So they end up with sort of an overall net charge, and that's why they're considered ions. And they kind of work like an ionic compound. And because they will hook up with metals, we kind of use like our type 1, type 2 a lot of times with them because the metals involved. Other questions on that? So why don't we try some here? All right, why don't we do Cu2SO4. Why don't we do Li3PO4. Why don't we do NaOH? And then why don't you do the formula for iron 2 hydrogen carbonate. Why don't you do potassium permanganate and only do calcium hydrogen sulfate. And let's do ammonium sulfide. All right. All right, names on the left and formulas on the right. I wrote them all around here so you can still see the table. So that should help you do it, I hope. And then we'll go through it. So 4. Lithium. Okay, so looking at these, we see copper, which is a metal. Again, when we look at this guy is sulfate, which is SO4 2-. In this case, we do need to figure out the charge on the copper, and we do need a Roman numeral. In this case, we have not one copper, but we do have 2 of them. And it's important to know that the charge on the sulfate is -2. That means in this case, each copper actually is +1, yes? And that means that the name here would actually be copper Roman numeral 1. And then we'd use the whole name of the polyatomic ion, which would be sulfate. Any questions on that one there? Looking here, we see Li, which is lithium. That is a metal. This guy here is phosphate, which is PO4 3-. Lithium is group number 1, which means it's really a type 1 metal. It has a fixed charge, which means we don't have to figure out the charge because we already know what it is. We just use the whole name like type 1 would be, lithium, and the whole name of our polyatomic ion, which would be phosphate in this particular case. Any questions on that one there? NaOH, Na is sodium, OH is OH-, which is a polyatomic ion. Here, sodium again is a type 1 metal, which means you don't really have to figure out the charge. We already should know that the charge is +1, and that means it would be sodium hydroxide, whole name of the polyatomic ion in this particular case. Any questions on that one there? Now, if I had, say, magnesium hydroxide, and I wanted to write the formula for magnesium hydroxide, magnesium is group number 2, which means it has a +2 charge. Hydroxide, as I wrote up here, is -1. So just like a normal ionic compound, right, we want to put these together to get us to 0 charge. On the left, the magnesium has a +2. On the right, the hydroxide has a -1, which means we need not one of these hydroxides, but we actually need 2 of them. So if we were to write this formula, it would be MgOH2. Do I write it like that? MgOH2. I actually do not, because that would imply that I have only 2 hydrogens and 1 oxygen, when in reality I have 2 oxygens and 2 hydrogens. So whenever you have more than one polyatomic ion, you do need to put parentheses around it and the number on the bottom to indicate how many you have. So the correct formula should look something like that, MgOH2. So multiple polyatomic ions, when you're writing the formula, you need to put parentheses around the polyatomic ion, number on the bottom right to indicate how many you have. If you have just one polyatomic ion, like we had in each of these cases over here, no parentheses needed. So parentheses when you have more than one. Any questions on that one there? All right, so going back here to our other ones that we want to write some names for, we have ammonium sulfide. So let's take a look at that. Ammonium sulfide. In this case, ammonium is NH4+. Sulfide is actually sulfur on the periodic table, which is group number 6, which has a -2 charge. In this particular case, we actually need more of the ammonium. We need 2 total, which means that is more than one of these polyatomic ions. So we do need to put parentheses around it, and a 2 on the bottom and 1 sulfur there to finish that guy up. Question on that formula? Then we had iron 2 hydrogen carbonate. So just like we did before, the iron 2 means we have an iron with a +2 charge. Hydrogen carbonate, which is also called bicarbonate, is a hydrogen and it's carbon, 3 oxygens with an overall charge of -1. So again, we want to get to 0. So we need not 1, but we need 2 of those hydrogen carbonates. That would give us an FeHCO3. Again, we need to put the 2 on the bottom because there is more than one of those polyatomic ions. Any questions on that one there? Yeah. Again, it's really an ionic compound when a polyatomic ion comes together with a metal or anybody else. So the overall time, whenever you take anything that's positive and negative together, you want it to equal 0, basically. Yeah. So we got to get it to 0. Other questions? All right, last couple here. Potassium permanganate. Potassium is group 1, which means it has a +1 charge. Permanganate, if you look on that list, is MnO4-. It's actually permanganate, manganate, manganite, and hypomanganite. It's a group of 4 that's actually related to each other. This ultimately is a +1 and -1 that's coming together, which gives you KMnO4. You just need one of everybody there, and that gives you potassium permanganate. Wonderful purple, turns everything purple. And lastly, we have calcium hydrogen carbonate here. So we have calcium hydrogen carbonate, which again is also bicarbonate. And in this case, or was that sulfate? Sulfate, maybe. Sulfate, thank you. Sulfate. So calcium is group 2 +2. Hydrogen sulfate is SSHSO4-. In this case, we need 2 of those guys to balance it out. Gives us CaHSO4 with a 2 in here. So as you can hopefully see here, really polyatomic ions are pretty much going to kind of follow, for the most part, type 1 or type 2. So if the metal needs a Roman numeral, you need to include it. If it doesn't, you don't. And obviously, if you have more than one polyatomic ion, you need to put parentheses around it. You need to learn the polyatomic ions, yes, the charges, the names, because that'll help you balance out everything that's on there. Any questions on polyatomic ion naming? All right, so we will stop here for today. So